5.2, dividing radicals and rationalizing. When we divide radicals, it's going to work just like when we multiplied radicals. We're going to divide the coefficients and divide the radicands separately. And you can simplify after, or you could try in some questions, simplifying first and then dividing. We've got a denominator, so of course we have to watch out for zeros in the denominator. Here's how I wrote the steps. Divide the coefficients, divide the radicands, and then try to simplify. However, you can change those steps based on the question. Our first example, we have the square root of 10 divided by the square root of 2. And we can combine these because we have the same index. Divide the coefficients. In this case, there's a 1 here and there's a 1 here, so 1 divided by 1 is 1. We still don't write it. And divide the radicands. So 10 divided by 2 is 5. Example 2. We'll divide the coefficients and then divide the radicands and see what happens. So 12 divided by 18. That gives us 2/3. We don't want to write things as a decimal, especially not a repeating decimal. Keep it as a mixed fraction. Then we'll divide the radicands, so 60 divided by 5. And that's 12. And now, last step is to simplify this radicand. Get out any perfect squares. There's a perfect square in there, it's 4. So first I'll write it with a perfect square in front of the non-perfect, and then I'll actually take the square root of that. So 2/3. The square root of 4 is 2, and the square root of 3 stays in there because it's irrational. And then we've got 4 divided by 3 times root 3. And this would be great. We could leave it like this. We could have the fraction all along there because this is in the numerator. We could also do something else with this one. We could take the square root of 3 and 3 here, and I'll use exponential form. I'll use an exponent to help us with this one. So the square root can be written as an exponent of 1/2. And the 3 in the denominator, it has nothing with it, so by default its exponent is 1. Now I can simplify that. So I'll have 4 in the numerator, and 1/2 minus 1 is negative 1/2. Or I could say I've got 1 whole one here, I've got a 1/2 that will cancel it here, that leaves me with a 1/2 down here. Now we'll come to this later on, but some people do not like radicals in the denominator. This is fine here, and this is also fine here. Next one. These two are different, and I can't put them together. I could try to simplify them first, or I could divide. So for this one, I'm just going to divide first. So first, the first term divided by 2 root 3. So 2 divided by 2 is 1. And root 18 divided by root 3 is root 6. Next one, 6 divided by 2 is 3. And 24 divided by 3 is 8. And now try to simplify. This was just 2 times 3, so that does not have any perfect squares. This does have a perfect square. Take it out. Square root of 4 is 2, times 3 is 6, and there we'd be good there. What if we simplified first? So I'm going to put an or here. There's a perfect square in 18. There's also a perfect square in 24. So you might be tempted to simplify those out. So the first one, it would be 2, 9 times 2 is 18, minus 6. Perfect square in here is 4. So 4 times 6. In the denominator, there's nothing to simplify. Now the square root of 9 is 3, so a 3 comes out. 3 times 2 is 6. So that can be written 6 root 2 minus the square root of 4 is 2. 2 times 6 is 12. And the square root of 6 still beside it. And in the denominator, the 2 root 3. And now we want to divide each term by 2 root 3. So 6 divided by 2 is 3. And we got root 2 divided by root 3. Root 2 divided by root 3. Minus 12 divided by 2 is 6. And root 6 divided by root 3 is root 2. Now you can see that the second term matches, but the first term looks different. This one is the square root of 6. This one is 3 root 2 divided by 3. So what can we do to make those look the same? Rationalizing the denominator means we want to rewrite an expression so that there's no more radical in the denominator. This is a skill that we need as we go on in math. We could also rationalize the numerator if we required that for some reason. Now, some people think that you can't write an expression with a radical in the denominator, and it's wrong if you do. This is an incorrect idea, and it comes from a long time ago before we had calculators. Before we had calculators, we used slide rules before my time, and it was very difficult or impossible to divide by a radical. And so they made a rule, don't leave a radical in the denominator. Nowadays, we have calculators, and there's no reason, we have no trouble dividing by a radical. And so there's no such rule that you can't have a radical in the denominator. That was just a man-made up thing. There's no mathematical reason for it. But let's see, we do need the skill, so let's see how we would do it. We have a root 7 here, and to get rid of a root 7, we need to multiply numerator and denominator by root 7. That way, we'll have a perfect square down here, 49. Or we can just skip that and say, hey, it's just 7. And 1 times root 7 is root 7. So that denominator has now been rationalized. It does not have a radical in it anymore. So if we have a monomial square root in the denominator, just a single term, okay, then we just multiply by that. How can we rationalize a denominator if it has a cubed root? And I also put a coefficient in here, just for good measure. Now, if we have a cubed root, I need a perfect cube down here. So if I try to do the trick at the beginning, multiply ones, I'm not going to end up with the perfect cube. And also, this 5 has nothing to do with it. Don't multiply by 5. You're just going to have to simplify it out in the end. We're only multiplying by the radical. So if we do it once, I'm just going to show you what we get. We don't have to show this intermediate step when we're doing it. We've got a cubed root of 3 in the numerator and 5 cubed root of 9. And we have not rationalized the denominator. There's still a radical there. So, like I was saying, we need to do it however many number of times to get a perfect cube, or in the first case, a perfect square. So, if we already have a perfect cube or perfect square, we don't need to, we just work with that. This one, multiply it once more, and we get the cubed root of 9, the 5 still just hanging out in the denominator, and the cubed root of 27. And now the cubed root of 27 is a perfect cube, it's 3. And so cubed root of 9 over 15. Now it still has a radical. So when we rationalize, we're not getting rid of the radical. We're just moving it to a different place in the equation. For these examples, we want to simplify, we want to rationalize the denominator, and we want to record any restrictions on the variables. Example 6, let's just divide. We've got no coefficients, So we'll just divide radicands. 24 divided by 3 is 8. And x squared divided by x is just x. Now we want to get the perfect square out of here. 8 has a perfect square, it's 4. So I'll just write that step. You don't need to separate it out and leave whatever else isn't perfect behind. The square root of 4 is 2, and the 2x is not perfect, so it's going to remain under the radical sign. And then since this is a square root, then our x value, if we want real numbers only, our x value needs to be greater than or equal to 0. Next one. We can't really divide these coefficients or these radicands. So let's just rationalize and see what happens from there. We've got a root 2, and we don't want a root 2 in the denominator. So I'm going to multiply top and bottom by root 2. That will create a perfect square here. 4, 10, and multiplying the radicands. And 3 and root 2 times root 2 is just 2. Now we see we can simplify. This 4 divided by 2 is 2. And there's our expression, simplified nicely. Our restriction on n, since n is under a square root, and if we wanted real numbers only, n needs to be greater than or equal to 0. And the last one, there's nothing we can divide here for y and 11 and 6, so we're going to rationalize the denominator. And I'll do it in one step this time. To get a perfect cube with 6, I need a 6 times 6. So I'll multiply by the cubed root of 36. 4, then we need 36 times 11 is 396 divided by the cubed root of 6 cubed, which is just 6. We can simplify, divide this by 2, divide this by 2. And it looks good. We have a y not under radical, but we do have it in the denominator, so y cannot equal 0. Now the other thing we might be cautious of is, oh dear, are there any perfect cubes in this large 396? And we can be confident we don't, because we made 396. It was 6 times 11. So there's no groups of 3 in there. For these examples, we want to rationalize, and if there's variables, record the restrictions on those variables. So for the first one, I'm going to try what we tried last time, and then I'm going to erase it because it won't work. What if we just multiplied by root 5 over root 5? I mean, that's what we did last time. This time we have a binomial. We have 2 terms down here in the denominator. In the numerator, everything looks fine. And in the denominator, we've got, hey, root 5 times, just like there's brackets here, root 5 times root 5, that's just 5, and root 5 times 7. Oh, man. So we did not rationalize the denominator. Whenever there's another term here, it's going to ruin this kind of plan for us. So we can't do that. Got to think of a different strategy, and that is conjugates. Root 5 minus root 7. Root 5 minus root 7. When we do it this way, in the numerator we can leave it apart. We don't need to combine it. In the denominator, it's like this. Okay. We got root 5 times root 5, it's 5. We got root 5 times negative 7, so negative 7 root 5. 7 times root 5, and 7 times negative 7. And now these two radicals cancel. And so we've rationalized our denominator. Let's try to simplify this up now. 5 minus 49. Looks like we can divide top and bottom by 11. So root 5 minus 7 over 4, negative 4. And that would be good. If we wanted to, we could put the negative in front, or we could divide the top and bottom by negative. Either one of these would be fine. So when there's a binomial in the denominator, then we'll multiply by the conjugate of that. Why? To get rid of radicals. Remember, the conjugate is the same thing, but the signs are reversed, and then we just end up with the first term squared and the last term squared, and that will get rid of it, as long as we're dealing with square roots. Next example. We've got a binomial again in the denominator, so we're going to have to multiply by the conjugate. Root 2 minus 1, root 2x minus 1. Multiply these out, so the first one here, square root of 12x squared. Let's put some brackets here to show these are binomials. Next one, minus root 6x minus 6 root 2x plus 6. In the denominator, we've got 2x, and then I'll skip this one. This one's minus and plus, so cancels, and then minus 1. And then we can simplify this. This is has a 4 in it, and this x squared is also perfect. We can take that out. So 2x, root 3, 6x, all the rest of the stuff stays the same. There's nothing we can do with this. So if we left the numerator not multiplied in, that would have been fine as well. X is greater than or equal to 0. Last example. This one looks like a binomial at first, but it's not really. The binomial is under the vinculum, and so this one is a single term. So rationalize it like you would single terms. Just multiply it by it once. No conjugate here, because it's all under the same radical sign. 3x, root 3x minus 1. In the denominator, we got rid of the radical. And then all we need is our restriction on the variable. Our variable is under the radical, and it's also in the denominator. So that means we have 3x minus 1 needing to be greater than 0 and not equal to 0. Do a bit of algebra here. 3x needs to be greater than 1 by adding 1 on both sides, and divide by 3 on both sides means x needs to be greater than 1/3. This one we have 2 terms in the denominator. So we'll have to use the conjugate. Notice we don't care what's in the numerator. There is a conjugate for the numerator, but we're not going to use it unless we want to rationalize the numerator instead. So multiply the numerator and the denominator by the conjugate of the denominator. Now doing some mental math here, I don't think anything will cancel or factor out, so we'll just leave the numerator as it is. In the last example, we did a lot of work multiplying it together. It didn't really get us anywhere. So we'll leave this one together. The denominator, 5x cubed minus, this one would be 2 times 2 is 4, times 2 is 8. Now we need the restrictions on the variables. We have an x under a square root, and that means that we need x to be greater than or equal to 0. Same thing in the denominator, but we do have to worry about the denominator as a whole. This expression here cannot equal 0. So root 5x cubed minus 2 root 2 cannot equal 0 either. Let's do some algebra so we can isolate for x. So we'll add 2 root 2 on both sides, and then divide by root 5 on both sides. So we got x cubed square root, and this side we just have 2 root 2 over root 5. Then we want to square both sides and cubed root both sides. So to get rid of that, square and cubed root. Square and cubed root. That will cancel this out. We're just left with x cannot equal. This squared is 8. This squared is 5. And we could leave that as an exponent of 1 over 3, or we could write cubed root like that. This was part of Algebra and Number 2, solving problems that involve operations on radicals. Here's some homework. Give it a try, see if you know what you're doing.